Welcome to Learning with UNP. In this session of Data Science and Mastering Machine Learning, we are going to understand about K nearest neighbors practical implementation on a project. In here, we are going to use KNN to solve a regression problem. The objective of this project is to build a predictive model using the KNN algorithm to predict the concrete compressive strength based on various input variables. By analyzing specific features from a dataset, we aim to determine the resulting strength of the concrete mix. Let me give you an overview of what exactly we will be doing in this project. In this project, we will write Python code to implement each step of the machine learning process. This project involves several key steps: loading and exploring the dataset, splitting the data into training and test set, building and training the KNN Regressor model, and evaluating the model's performance using appropriate metrics. We will utilize a concrete compressive strength dataset which contains various predictors to train and test our model. All coding will be done using popular libraries such as Pandas, NumPy, scikit-learn, and matplotlib. Let's begin with understanding the dataset. Concrete compressive strength. A key measure in civil engineering depends on its age and the mix of ingredients used. This dataset has 1030 number of instances and 9 number of attributes, in which attribute breakdowns 8 quantitative input variables and 1 quantitative output variable. There is no missing data, making it suitable for regression analysis to predict the strength based on other variables. Let's look at independent variables along with the explanation of each variable. Cement, amount in kg per cubic meter. Blast furnace slag, amount in kg per cubic meter. Fly ash, amount in kg per cubic meter. Water, amount in kg per cubic meter. Super plasticizer, amount in kg per cubic meter. Coarse aggregate, amount in kg per cubic meter. Fine aggregate, amount in kg per cubic meter. Age, number of days 1 to 365 since mixing. The output variable is the concrete compressive strength measured in megapascals MPa, which indicates the load bearing capacity of the concrete. To begin our project, the first step is to load the concrete dataset into our Python environment. We will use the pandas library, which is widely used for data manipulation and analysis in Python. Below are the detailed steps and code to load the dataset. First, we'll import necessary libraries like pandas and numpy. Then, we will load the dataset from a CSV file into a pandas data frame, which allows easy data manipulation and exploration. Finally, we will inspect the first few rows of the data frame to understand its structure and content. Here is how we import various libraries. NumPy as NP for numerical operations, Pandas as PD for data manipulation and analysis, Seaborn as SNS for statistical data visualization, Matplotlib to display plots in line in Jupyter notebooks. Now, we will load the concrete dataset into a pandas data frame using the read_csv function specifying the file path. This allows us to easily manipulate and analyze the data. In here, data.shape gives the number of rows and columns in the dataset data. This output indicates our dataset comprises 1030 rows, which are instances, and 9 attributes, which are columns. These 9 attributes include 8 features such as the amounts of cement, blast furnace slag, fly ash, water, super plasticizer, coarse aggregate, fine aggregate, and age, along with one target variable indicating the concrete compressive strength. Before using KNN algorithm, you may need to pre-process your data if required. This can include cleaning the data, handling missing values, and encoding categorical variable. This line of code checks for missing values in each column of the data frame data and sums them up. In this dataset, there are no missing values in any of the columns, as indicated by output of zeros for each attribute. After checking carefully, we found no missing values in our dataset, meaning all entries have all the necessary information. Also, all the data is in numbers already, so we don't need to change anything about how it is stored. This makes it easier for us to use the KNN algorithm directly without having to prepare the data first. Now, let's move on to the next step of separating features. To prepare our data for the KNN regression model, we need to separate the features from the target variable. The feature X include all the ingredients and age of the concrete, while The target variable y is the concrete compressive strength. We do this by creating X, which contains all columns except concrete compressive strength, and Y, which contains only the concrete compressive strength column. This separation is crucial for training the KNN model as it allows the algorithm to learn from the input features and predict the target variable. Here is the code of it. Now let's look at train test split method. To evaluate our KNN regression model effectively, we split the dataset into training and testing sets using the train test split function from the scikit-learn.model underscore selection module. This process creates four arrays: xtrain, xtest, ytrain, ytest. Xtrain and ytrain. These arrays contain the features and target values for the training set, which is used to train the KNN model. Xtest and ytest. These arrays hold the features and target values for the testing set, which is used to evaluate the model's performance on unseen data. We will use the test size parameter set to 0.3 to allocate 30% of the data to the test set, with the remaining 70% going to the training set. The random state parameter ensures that the data split is reproducible, meaning the split will be the same each time we run the code with the same value for consistency. This method helps us train the model on one portion of the data and validate its performance on another, ensuring the model's reliability and effectiveness. The code is shown here. Over here, let's look at model building. In K nearest neighbors, we have two main types, KNN Regressor and KNN Classifier. The choice between them depends on whether we are predicting continuous values or class labels. Since our goal is to predict the concrete compressive strength, a continuous value, we use the KNN Regressor. We start by importing the necessary libraries from sklearn.neighbors, specifically the kneighbors regressor module. This module provides the tools to implement the KNN algorithm for regression task. It allows us to construct the KNN regressor, fit it to our training data, make predictions on new data, and evaluate the model's performance. Importing this library ensures we have everything needed to build and analyze our KNN model efficiently. The KNN model is set up with specific parameters, particularly in neighbors, which dictates how many neighboring data points the model will consider when making predictions. In this instance, the model is configured to utilize 5 nearest neighbors. This parameter choice significantly impacts how the model assesses similarity between data points and directly affects both the accuracy of predictions and the computational efficiency of the algorithm. Once initialized, the KNN model is trained using the training data, xtrain and ytrain. During this training process, the model learns the relationships between the features and their corresponding target values. By understanding these patterns, the model optimizes its ability to accurately predict the target variable for new unseen data. After the KNN model has been fitted with the training data, it is ready to make predictions on new data points using the testing data, xtest. The predict method applies the trained model to generate predictions for the target variable ypred. These predictions reflect the KNN model's estimations of the outcomes for each corresponding input in the testing dataset based on the patterns learned during training. This step is essential for preparing the model to make informed predictions. Predictive performance. This step allows us to assess how well the model generalizes to unseen data and evaluate its predictive performance. This data frame compares the model's predicted values ypred with the actual values ytest from the testing dataset. By reviewing this comparison, we can assess how accurately the KNN model predicts concrete compressive strength. This evaluation helps identify strengths and areas needing improvement, guiding decisions on deploying the model effectively in real-world scenarios. Let's move on to understanding the evaluation metrics. To evaluate the model's performance, use metrics such as mean absolute error (MAE), mean squared error (MSE), R squared, and other metrics. These metrics will help you understand how well the model is predicting the target values. The R square score function from sklearn.metrics computes the R squared score of our KNN regressor model by comparing the predicted values ypred with the actual values ytest. It measures how well the model's predictions approximate the actual data points, providing an indication of the proportion of variance in the dependent variable that is predictable from the independent variables. This code yields accuracy as approximately 68%. The mean absolute error function from scikit-learn metrics calculates the mean absolute error MAE between the predicted values ypred and the actual values ytest. This metric measures the average magnitude of the errors in a set of predictions without considering their direction, providing an indication of the model's accuracy in terms of the average absolute difference between predicted and actual values. This is the code which outputs approximately 7.3. The mean squared error function from scikit-learn metrics calculates the mean squared error MSE between the predicted values ypred and the actual values ytest. This metric measures the average of the squares of the errors, providing an indication of the model's accuracy in terms of average squared difference between predicted and actual values. Here is the code of it, which yields accuracy as approximately 91%. By computing the root mean squared error RMSE from the mean squared error MSE, we obtain a measure of the average magnitude of the errors in the same units as the target variable. This involves first calculating the MSE with mean squared error ytest ypred, then taking its square root using np dot square root of MSE, which gives us the RMSE. This is the code of it, which outputs approximately as 9.5. The mean absolute percentage error function from scikit-learn metrics calculates the mean absolute percentage error MAPE between the predicted values ypred and the actual values ytest. This metric measures the average absolute percentage difference between predicted and actual values, providing an indication of the model's accuracy in terms of the relative error. The MAPE can be expressed as a percentage by multiplying the result by 100. Here is the code of it. Here, we create a scatter plot showing the relationship between the amount of water in the concrete mix and the concrete compressive strength. This scatter plot compares two things: the amount of water in concrete mixes shown by blue dots and how strong the concrete is as a result. The red dot represent what our KNN model predicts the strength will be based on the water content. This lets us see how well our model predictions match up with actual observations, helping us understand its accuracy in estimating concrete strength. If the KNN model's performance isn't satisfactory, adjusting the number of neighbors k can help. By experimenting with different values of k and repeating the training and evaluation process, you can find the optimal configuration for your dataset. A smaller k may capture more detail but be prone to noise, while a larger k may oversmooth the data. Finding the right balance can improve the model's accuracy in predicting concrete compressive strength based on your specific dataset and its characteristics. This is all about today's lecture. See you in the next lecture. Thank you.